All right, moving into our last module. This is module 10, and we're looking at change detection. So, so this is really why we do remote sensing. We want to see changes over time. We might do a lot of analysis as a capture of that moment, but over time we want to be able to see changes or see what is happening, and that's really the biggest strength of change or of remote sensing is this change detection method. Or so we're going to take a look at this and in terms of the objectives. You are also going to be taking your interpretations, and this is your entire final project, is all of this change detection stuff. So starting with this one, this is the primary purpose of remote sensing. This is why we do change detection. Just that it is considered a post-processing step. So going back to the 4 Ps, right? The digital image processing. So we had pre-processing, processing and analysis, post-processing, and presentation. This is a post-processing step. The reason it's post-processing is because it allows for our whoever, our client, to make decisions based on the changes that they are seeing. We almost always apply this to transformations, not to raw bands, and we also apply this to classifications. So there are 2 types of results. There is a qualitative result and there is quantitative. So qualitative means that there's no numerical result. It's merely just seeing class changes or changes that we can point out in a particular area. Quantitative means that I can actually give numbers to it. So the applications are limitless, as you found out probably on your own. Just when I say, okay, you're going to take a look at changes in the environment, there's so much that you can look at. So anything that can change, whether it be urban development, flooding, volcanic breathing, there's everything. So application-wise, I can't even begin to list all of them. It would be almost impossible. So there are a few change detection methods that I want you to attempt in your final project. And so this is the theory behind them. The first one is known as a right function memory insertion. It is just a really fancy way to say, hey, go create a composite. So what you're doing is you're using 2 dates. So you're using the old version and the new version, and you're going to make sure that the dates are all in one single database, because that's the way that the composites work. Then you're going to decide which transformation you want to look at. So for example, here I'm showing NDVI. So I chose NDVI because I want to show vegetation changes, and then I'm going to create a composite with that. So in my red slot for RGB, I'm going to put like NDVI 216, and then I'm going to click it again for my green. So it ends up becoming 2 of the slots are filled with the NDVI 2016 from 3 years before, and then now I've got NDVI 2019, which is the newer version of my image. So what happens as I make these changes? So if I increase the value of 2016 and I increase the value of 2019, I get white. So there's no change, right? Because they both increased, and they both increased at the exact same rate. So therefore, I'm going to get a white pixel. If I increase my 2016 value and I decrease my 2019 value, I end up with a yellow. So you can see how if I put together red and green, I end up with the color of yellow. So that's why it's going to show as yellow, is because this is higher than this one. Now if the 2016 value is lower and the 2019 value is higher, now I'm going to have blue, and that's going to show that the value increased. If both of them have gone down, or they're both fairly low, then the black. Now when I say go down and up, I mean I'm just referring to if I was changing the numbers. So high value white, high value yellow, low value high value blue, and then low value black. So when I'm referring to positive and negative change here, this is giving me the opportunity to say it went down. So NDVI in this case, the health of the vegetation has gone down if I'm seeing yellow. If I see that everything is blue, then I can say that the health of the vegetation has gone up. With this one, I see both qualitative and quantitative results. So the qualitative results within this is looking at the colors and being like, oh, this one went down and this area went up. The quantitative results is the actual pixels that I've picked, and I can say this is the value of the NDVI in this here, and this is the value of the NDVI in this here, and so therefore I can actually like look at those numbers themselves. Every time you do change detection, you need to give some examples of the pixels, especially in these numerical ones. So then there's two others. They're pretty straightforward. So temporal image differencing means I take one image and I subtract it from the other. So if I'm using my NDVI, I always take my newest image and I subtract the oldest image. So if I do that, if I end up with a negative value, that means that the value itself, like for in this case NDVI, it has gone down in health of vegetation. So I'm ending up with this negative change or negative value. If it says 0, then I've had absolutely no change. And if it is positive, then we have a positive change. So it means that the 2019 has actually gone up for NDVI. This is a numerical analysis entirely. You need to provide numerical examples of the areas of your interest. Temporal image ratio, this is looking at the two ratios, or the two images and providing a ratio for it. So the 2019 divided by 2016, if it is less than 1, it means that the 2016 value was higher, so therefore the health of vegetation has gone down. If it is equal to 1, it means that they're the same, and there's been no change between them. And if it is greater than 1, then I have an increase in my NDVI value. Using these three values, I get a number, so therefore I need to use examples of pixels. Then moving away from the numerical methods, we can look at classification methods. So we have a multi-temporal classification, and this one's kind of a unique one. So I have to make sure that both of my images are in the same database, as all of these are. And I'm going to classify both, or the whole thing, that whole database. I'm just going to run an unsupervised classification, and I'm going to use 3 classes. So if I do unsupervised, I can do supervised as well. But if I do unsupervised, what it's going to show is that, hey, here is my 2016 values, all of them, because I'm running a spectral analysis, right, with unsupervised classification. And then it went down. Everything dropped in 2019. So when I do this, make sure that it's old to new, right? So you set up your database starting with the old values and going to the new values. It's going to say, hey, look, this is different and this is different than this one. Therefore, this is now showing a negative change. And it's looking at individual pixels to do this. So every pixel gets assigned this value. Then, or like one of these values. Then we have a no change, which means that it's just straight across. It sees no difference between them. And then we have a positive change, which means that it's gone up. All the values have gone up. The benefit of doing the classification is that I can examine my entire database at the same time. The disadvantage of doing this is that I can't really define it based on, especially the unsupervised, I don't really have any accuracy measure. And the validation of it can kind of be challenging, especially if you don't have previous year's data. The supervised classification uses the same 3 classes, but you actually do the training areas, right? So we just go back to supervised classification. This method is absolutely no different than running classifications like you would normally do. The only difference is that I don't have to worry about Anderson land cover type words, and I'm only using 3 classes. So what you have to do in the end is either A, with unsupervised classification, figure out how did it change, like what changed and everything else. And then the other one is the supervised classification, which I have to do that at the beginning. This is generally a qualitative assessment. You can take a look at individual pixel spectral signatures based on both databases, but And that is actually sometimes really interesting. That might actually help you in making that decision. So you might be like, hey, look, there is a huge change in one peak, and then you got to figure out which that class is. So if you pull up the spectral signatures of the database for the pixel you are looking at, that will help you. That gives you a little bit more of a quantitative measure, but not truly. Then we have something called a post classification. This is also known as thematic change detection. So what this does is it says, hey, this class changed to this class. This is really the best thing to do with supervised classification because you know your accuracy and you know what those classifications are. So you have to run 2 supervised classifications. Once you have 2 supervised classifications done, one for one year, one for the other year, then you can put it into this thematic classification workflow. And then the output is the different kinds of classification. So it says, hey, class 1 changed to class 2. Class 1 changed to class 3. Class 1 changed to class 4. And then it's like, oh, class 5 changed to class 1. So it goes back and does that and tells you every single combination that you can possibly have. So if you have 15 classes, this becomes an enormous amount of legend work. So again, I would suggest making really small area, saying, hey, I want to run this, but I'm only going to apply it on a small resized image, and I'm only going to have like 3 classes rather than the 10. So that may help you a little bit in your when you're doing your processing for your final project. But post classification is always interesting to be able to say, hey, these trees actually turned to burn scar, and it's easy to classify that way. So comparing them, I'm just going to show some images here using the different ones. So this is what often it looks like when we use right function memory insertion. So you can see that the red, it's actually yellow. If it's done, you can change this up. Of course, I'm only showing one standard. So they were trying to show something hot in this case and change. So they had the new or old image. I don't have a legend over here telling me what they did, but these are the hot, so it's probably the increase in value in an area, maybe for forest fires. And they would have said, okay, maybe 2019 or 2020 was that particular year, and that was put in red. And then maybe 2018 was they put that in the green and blue slot. So that's why it's kind of like a cyan. So this one's a little bit mixed up, and that's okay. You can do that with the WFMI. You can change up whatever you like, whatever combination you like. Sometimes it's a little bit more intuitive to change the colors rather than having blue and yellow. Especially if you have vegetation, you might want to increase, like say, hey, I want the new one to be the green and the other two, the old one, to be red and blue. So you can change it up how you like, but this is just another example of that. Image differencing. Here we can see where the increases are. Vertical distance changes. This is in vertical. You won't actually see that in your images. You won't be able to determine height differences, but this is the same idea. So you would either provide a legend of all the different color changes, or you would identify a particular pixel and say this is what the value is. So you can see how this shows the vertical change anyways. So that's image differencing. Image ratios are kind of weird because ratios are all in decimals. So if you do image ratios, make sure that you identify areas and use examples. Why did you use a ratio? Does it make more sense? So showing here where the fire is and how it changed throughout in that ratio for what they were using for that change detection. So that gives you a little bit of a concept there. And then the values that you would end up with, and they're trying to represent those across the image. You always need to have a legend with these so that somebody knows what they're looking at. Then we have multi-temporal classification as an example here. So I apologize about the poor quality. So we have natural vegetation loss, and then other changes, and then stable vegetation. Notice that this is not saying positive or negative change. It's actually a specific term, you have to do the same with yours. Like, oh, I'm looking at vegetation loss in this area, or oh, I'm looking at an increase in urban area, or I'm looking at a flooding situation, like increase of water in that area. That is, you need to be very specific about this, and that's what you can see here. Again, that legend is important. Here's another legend. This is exactly what post-classification change detection looks like. Shows a legend showing deep water to vegetation, or well, vegetation to settlement, and you can see how that has changed in over, the 30 years. So again, it's just a simple classification change, one class to another, and that's post-classification change detection. Again, these legends are very, very important. So quality, there are two different ways to assess quality. There is visually and numerically. As always, you need to include both of them if you can. So visually, you just look. Go back to your old image, like the original image, and see if that makes sense. Does it make sense if I switch between these three, or even just put up all three in the window and try to compare them? You can use portals or transparency as well, or different windows, but you need to talk about that, like visually what is happening. Can you see, does that actually capture the differences that you are seeing? Then numerically, if you're doing differencing and ratios, you actually need to have a numerical analysis. So you can give means, standard deviations, and variances. That's kind of the average, like a normal statistical analysis. You can also calculate overall number of pixels that fall within that particular number. You can have a threshold, percentages of change. So, if you have a total difference, like the largest difference versus the smallest, what percentage is it showing? There's a lot of math that you can do with this and very simple statistics that you can do with this. And of course, there's always like goodness of fits and stuff, but I don't teach you that yet. I teach you that next semester. So you guys get out of that numerical analysis. But if you're doing differencing and ratios, I expect to see these kinds of statistics showing up. Then we have the quality assessment as well for classifications. So confusion matrices. If you did a supervised classification, I want to see that. And you can, if you did the thematic class, you can overlay both of your images and look at how your polygons fit with each other. Again, there is a special portal to do that. So if that's something you want to look at, then let me know and I can help you out with it. But I need to see these producers and users accuracies. So if you drew an area saying this area has changed, this area has not changed, this one was a positive change, I want to see those polygons, and I want you to run this confusion matrix. If you're doing the thematic classification, it actually comes with its own statistics file, so you can check that out. But always provide values. It's so important that you provide values, because if you don't provide values, then it means nothing. So statistics is always really important, and just giving examples. Oh, this is this one, this is this one. So the actual applications here, how to choose a change detection algorithm, because these make great exam questions, hint, hint. So how would you choose a change detection method and being able to justify it? So does it require a calculation in the end? Do you need numbers in the end? If I'm calculating changes in yield of a crop over the last 5 years, I kind of need a calculation. So doing a thematic change does not do me any good. And do I need numbers? So if I'm looking at the change of the forestries, maybe not that. What would be a good example? The change of a grassland, right? So if I'm looking at grasslands and I'm looking at it, has there been an increase in bushes? Do I need numbers for that? Or am I just looking for the bush count? Am I trying to visualize that location? Of course, remote sensing is all about visualization. But if I'm more concerned about the yield of a crop, and I want to see how the yields have changed over the years, then I'm really trying to get numbers. I'll show the crop and be like, here's what it looks like, but that's not my primary goal. Let's say I'm looking at bears going through an area and we're trying to track bears, and so we have GPS colors on them, or we're kind of following them around. Where are the berries? Where are the berry bushes? How have they changed over the years? Have you seen an increase in berry bushes somewhere? And then do the grizzlies go down in that area, right? That I am trying to visualize a location. That's important to me. So do I need to know the name of the change? So do I need to know, did it change from this value to this value? Or am I just looking at numbers of it? Do I need that thematic information for it? Then what do we want to show the client? What's the easiest way to interpret it? Which algorithm is actually showing the change the most accurately? Is it one better than the other? Is there something about the change detection that I'm not actually capturing? And so forth. There's many, many, many questions. So you have to ask yourself all these questions before you choose a change detection algorithm. And because it's easier is not an answer. All right. So you need to have some really valid backup for that. Then some examples. So for example, fire scars. Let's say if I'm looking and I'm trying to monitor fire scars and how they're recovering. I am looking for a thematic change to show the location of where the fire scars actually are. And then I'm going to use a ratio or difference to show the vegetation health in those scar areas. So is my biomass increasing? Are the leaf area indexes increasing? What kind of tree what kind of tree would be thematic? So that would be the change. What kind of new trees are growing in that area? That depends on your scope of that fire scar, right? Sea ice reduction, that's another one. There is a thematic change to show ice versus water, right? That's a class change. I might need to do some differencing to show ice thickness change. And you do that with microwaves, but can't really do that otherwise. If you are trying to calculate the actual area, again, that's not so much a case of needing to difference, because the actual spectral changes is not the of interest, right? So we're actually more, if you're saying, oh, I want to calculate the area, you can do that with a class change. You don't need to do a differencing for that, because that's not going to give you the answer. What about desertification of an area? It's drying out. So thematic changes show the location, vegetation to sand, right? Differencing to calculate the moisture reduction. How much less water is there? There could be vegetation health as well, could fall into that one. Vegetation is always kind of a big one. There's also calculations of like soil indexes. So that might be a ratio that you might be looking at, two different indices and trying to compare them. And last one, another example is flood mapping. You showing the area. Do the numbers matter? Probably not, because you really can't calculate the volume of the water. You're more worried about the area. I can always do that like on a map. I can calculate areas on maps. So areas do not need differencing or ratios. Okay, so change of horizontal area does not matter in terms of that. What I'm looking for here is differencing in terms of the value of the pixel. That is why I would do differencing or ratio. So otherwise most of it is thematic. So is it changing or not? So again, numbers won't assist in flood mapping. You really could look at vegetation stuff. That's kind of stretching it though, because I'm looking for the flood of the water. I'm not looking for, how much sediment is in the water when it floods. Well, I'm not looking for that because I'm mapping it, right? I'm not mapping the water. So again, you really need to take some time to think through, why do I choose the change detection method that I do? And then from there, you're going to get a much better result and a much more valid result than just doing whatever just because it seems like fun. So that pretty much wraps it up. That's it. We're done. No more modules and listening to me on for remote sensing anyways. So if you've blown through all of these, you've probably spent a good like 20 hours of your life listening to them. Um, so this is, that wraps up everything from remote sensing. And for your final projects, please make sure you guys get those in. Please apply what you have learned from this module in your final project, because that is what I am using to mark you in this module. So that is everything, and I wish you luck for the rest of the semester, and I'm looking forward to all of your interactions on, well, that you have been giving me, and possibly online for the next few weeks, depending on how soon you did this module. And then good luck on your final exams.